I'll be here all week. Okay, on and off again. All right, Lab 9. So the whole point of Lab 9 is to use our balanced chemical formulas, our chemical writing, our stoichiometry to identify what our white salt is. Now, I'm going to give you either A or B. Okay? We don't know what A or B is. You're trying to figure that out. So I'm going to give you sample A or B. They could either be sodium. Okay, did you get a staple or no?
Yeah.
Okay, sodium, hydrogen. There's a couple of decoys up there that don't work, so sodium hydrogen carbonate. And this is a fancy word for baking soda. Okay, sometimes I call it sodium bicarbonate, but it's baking soda. Okay, and there's a reason for that. This is, so you're either going to have sample A or B could either be sodium hydrogen carbonate, baking soda, or you can have sodium carbonate, which is called washing soda. You can actually buy that in the laundry aisle of Stop and Shop or wherever you shop, okay? And you can buy washing soda, and if you look at the chemical, it's sodium carbonate, okay? Now, we're going to react hydrochloric acid to both of these, all right? And we're going to drive this reaction to completion, and I hope you understand what that means. So this is going to be the excess chemical. We're going to keep adding hydrochloric acid to our baking soda or washing soda until the reaction stops. Now, how do we know it stops? Well, there's a particular product it makes. It makes CO2 gas. We're going to learn an acid-base chemistry that we're doing next in our tour of stoichiometry, okay, that things that have carbonates in the presence of acids decompose. We'll learn why in acid-base chemistry coming up starting this week. But in any case, when you add an acid to carbonates, CO2 gas is going to be released. And if a gas is formed in a solution, as you can see, you're going to see fizzing and bubbling, okay? So the fizzing that you're going to see is the CO2 gas being liberated. Because it's leaving the reaction container, equilibrium cannot be what? Established. So this thing is a completion reaction, and we're going to keep adding hydrochloric acid until the fizzing stops. Once the fizzing stops, we know we have driven all of this into the products. Now there's more products here. If there wasn't any, we couldn't do this lab because we need one of the products to figure out which one we have. So the star of the show, of course, it's the star of the show is sodium chloride. And we should give it its own unique color, okay? Sodium chloride. Is this purple or is this blue?
It's blue.
Okay, sorry to be a blue color there, trying to be neutral. And of course, water. So these are the products. Because the sodium chloride is going to leave the container, we're going to be left with, in our reaction vessel, hey, salt water, sodium chloride and water. And now, I say salt, you say anything ionic. Salt, anything ionic. These are salts too, okay? Everyone thinks salt is sodium chloride. It's one type of salt, okay? Any case. So we're going to be left with is a solution of sodium chloride and water and some excess hydrochloric acid, okay? Now, these reactions are very similar, but not the same, okay? So what we're going to do is we're going to take an evaporating dish, and it looks something like this. It's a porcelain dish with a spout, okay? It looks like almost like a duck that I cut in half with no body, but in any case, it's called an evaporating dish. And in this evaporating dish, I'll write that, evaporating dish, we're going to mask that out. Not only am I going to mask that out, I'm also going to add a watch glass. We know what that is. It's a piece of glass, it's conical. So this is going to be a watch glass. I know I don't have that in the lab we'll just add that to your data section. So you're going to measure an evaporating dish and a watch glass with your scale that's on your bench. Okay? Now, after you've measured your empty container, okay, you're going to add either sodium carbonate or sodium hydrogen carbonate. You don't know which one. It's either A or B. You don't know which one, so you're going to write down in your data section, hey, do I have A or B? Okay? I'm going to give it to you. You'll choose, I want sample A or B. It's one of the two. Okay. Then you're going to add hydrochloric acid to the evaporating dish, and you're going to keep adding until the fizzing stops. And so we're going to get excess hydrochloric acid. Our limiting reagent, of course, is our two initial compounds. Everything we've learned so far. Okay? So we're going to keep adding the acid until, and we'll see the fizzing, and then once the fizzing stops, we know we've driven it to completion. So we're going to have essentially salt water solution with excess hydrochloric acid. Okay? And that's what this is here now. All right. What we're going to do to recover the sodium chloride is that we're going to heat the evaporating dish. So we're going to put the cover or the watch glass on top of the solution. So we're going to have this watch glass again, this evaporating dish with the watch glass conical kind of down, convex side down to cover this. And the reason for the watch glass is that we're going to heat. Usually I heat for a couple days really, really and warm so it evaporates off very gently. But since we're in a rush to get this done today, we're going to heat violently. We're going to turn the hot plates on 550. I'm going to drop the watch glass right on top. So there's still going to be a little opening here so that the water vapor can leave. But the watch glass is there to trap any of the water or splattering of the salt. The water is going to evaporate. There's going to be splattering of salt water. Eventually you're going to have salt on the top or the bottom of the watch glass, and of course inside the evaporating dish. Okay, so we're going to basically heat, and because it's called an evaporating dish, we're going to evaporate off the water and the excess hydrochloric acid to reclaim the dried NaCl. It's kind of cool. Okay, so we're going to heat, and we're going to heat for a while, and then we're going to basically have crystals of sodium chloride. Okay, on the top too. It won't be black. All right, and so once it's dried, and it'll be about 10 or 15 minutes, we're going to, once we cool it, we're going to heat it again, subtract out the dry evaporating dish and the what? The watch glass, and you will get your experimental mass of NaCl in grams. Okay, so what do we do with that? Okay, what do we do with that? All right, if you go to your conclusion page, it's the last page. Okay, here's what you do. I have given you these two reactions. I don't know which one's first or second, but I think this one might be first. I want you to write the chemical formula. If you don't know what hydrogen carbonate is, you go to table E or F of your Regents chemistry table. Same thing, these are salts. Sodium is the metal in front. This is a negative ion here. Write the chemical formula. Then I want you to balance. You do the same thing for this one. Write the chemical formula and then balance. You will notice, party people, that there will be a different stoichiometric ratio here of NaCl. These reactions are very, very similar, but not the same. One of these two will have a different stoichiometric ratio for NaCl, which means what? We're going to produce more NaCl for one of the two salts. So what you're going to do for number 1 and 2 on the conclusion page is write their correct chemical formula, balance, and then you're going to assume you have this salt, given the initial grams of your A and B that you started with, you're going to calculate with stoichiometry how many grams of NaCl I should produce, assuming it was sodium hydrogen carbonate. And for number 2, you do the same thing. Take the grams of your starting material after you subtracted out the evaporating dish and whatever you had to do there, and then calculate using the correctly balanced chemical equation how many grams of sodium chloride I should produce, assuming it was that. And once you have those two masses of sodium chloride, see which one matches up best with this value here. It will be very close, okay? So using the stoichiometry, assuming you have each one, compare your experimental mass to one of the two masses that it best closely resembles or approximates, and that'll tell you which salt you have, okay? And then the last little piece, really simple, the last little question you can Q out, right? You can Q it out, W it out, or if you have to X it out, okay? So take the last question and do what you got to do, letter it out, and I want you to replace the last question with a percent yield calculation. Give me the percent yield. Now that you have your experimental mass, and now that you have what? One of these two is going to be your theoretical, the best matches, do a percent yield. Now I'm interested to see if you get under 100. I would expect you would, because we're going to lose some of that salt. Probably out. There's going to be some salt that splatters out, or two, these guys weren't what? 100% pure. Okay? That's the lab. It's pretty simple. You guys can finish it in class and hand it in today. Make sure you have units. All right? All right, so we'll start. Whenever you're ready. That's the lab. All right? Those at home. Oh, before we begin, if I haven't already, let me give you the objectives. Okay? Number 1, 2. Determine whether your sample is either sodium hydrogen carbonate or sodium carbonate. Identify the unknown sample as either sodium hydrogen carbonate or sodium carbonate. I kind of like my rephrased one better. But whatever works for you. Number 2, separate a mixture by evaporation. You learned this summer that sodium chloride dissolved in water is a solution. And you could separate a solution, at least the solute, by evaporating off the water. It's what the indigenous people did, or it's what we did as earlier settlers to get salt. Salt was an important product for civilization. For meat to not spoil, we would salt it or smoke it, okay? So we would go to the salt water in big pots and boil off the water and recover the salt, okay? So separating a solution by evaporation is an important separatory technique, okay? And it's a physical change. Now, number 3, to calculate the percent yield. I don't need a percent error, just a percent yield. And those are the 3 objectives. And that, my friends, is all the instructions you need for the lab. I do suspect that your percent yield will be below 100, okay, because of loss of some of the splattering, because we're going to heat pretty violently. If we were doing this over a 2-day period, I just put it on 50 and it comes back nice. So we're going to get this done today, all right? But one thing it's kind of cool is, and I don't know if we're going to get there because we're going to heat pretty violently, but if it heats slowly, you get these beautiful crystals. Okay, I want to show you the crystals that we do get sometimes. And here's an example of sodium chloride crystals that are recovered in the reaction. I'll put this on the big screen here. Maybe, maybe not. And let's focus. That didn't do anything. Got it. Oh, it's too close. All right, so these are some beautiful crystals. All right, I don't know if you can see from the screen, but these are very cubic. All right, these are pretty cool crystals. And they're squares. And they're square because they take a simple cubic structure. Okay, their structure is this right here. Sodium chloride. This is an example of a 1-to-1 salt. So the simple cubic structures are right there. Nice square. It's kind of cool. All right. Any case, without further frost, you can continue. You can start. Everything you need is back on your bench, and ready, set, go.